In this video, I want to try and give an overview of port forwarding and how it works and why it's used in the first place. This is a pretty advanced concept in terms of networking because to understand port forwarding, you also have to understand network address translation, or NAT for short. That's because port forwarding is actually a function of NAT. So without the context of NAT, port forwarding doesn't really make any sense. So I'm going to start off by explaining network address translation, going into port forwarding after that, and then I'll go into do some real-world examples of how it would work. So if you watched some of the previous videos, this might look somewhat familiar. This is a general layout of how a network would work in a home or small business situation. You'd have your devices that you're trying to connect to the internet. In this case, a couple PCs, maybe a phone. Generally, these would be on Wi-Fi, but for now, let's just say they're plugged in. It doesn't really matter. In terms of this layout, it doesn't matter what these are connected to at this point. This switch is then connected to the router, which then is able to send the information up to the internet. And the internet, it can take all kinds of different paths, and eventually it will end up at some sort, like a server that you're trying to access a website. And in this case, it could be something like this, where you send traffic from your PC, goes up to the switch, to the router, to the internet, and you want to get to, let's just say, actually, let's say this is a server. And your request would come through the internet, whatever path it may take, down to the router, which this router then routes to the switch, and then switch to the server. You can see the path that the packets are taking through this. In this case, though, there are technically 3 different networks at work here in this particular situation. And you can draw them out here. Actually, that's not a part of it. It would be more like this. Then this. Then you have your third one here. So these are 3 logically different networks that the routers are trying to route between. In this case, you have, these would be considered local area networks, where all your computers and stuff would be connected to the internet. This would also be a local area network, and this would be the wide area network. And in this situation, each 3 of these bubbles here are going to have their own address space. The router's job is to act like a post office. It's taking packets. You can kind of consider this being like this, each of these bubbles being a neighborhood, and the router's acting like a post office between them. So it's taking packets coming up from the PCs, figuring out where they're trying to go, and then sending them into the path, sending them along the path that will eventually lead them to their destination. Now, in an ideal world, each of these devices would have their own unique, globally unique address. There wouldn't be any 2 machines basically in the world that would have a similar IP address, which would mean that if this PC was trying to talk to this server, it could send it directly to this server's IP address. Unfortunately, that's not how it works with IPv4, which is the currently still the standard for internet protocol and internet routing. So with IPv4, there is a set limit to the amount of unique IP addresses that can exist. And that's just a legacy situation. Back when the internet was first being designed, there weren't that many computers around, so the setup that they came up with made sense at the time, but was pretty quickly outgrown in today's standard. So in IPv4, each IP address is going to have a format that looks like this, and each of these ends here would represent a single digit number. And the minimum address is all zeros, and the maximum address is all 255. So that's because each of these numbers corresponds to 1 binary digit. And binary digits have a maximum range of 0 to 255. So in IPv4, it's always going to be in the format of 4 binary digits, which range in value from 0 to 255. So there's actually 256 unique values per digit. So we can find out exactly how many unique IP addresses there are in existence by doing 256 to the power of 4, which gives you about 4 billion unique addresses. So 4 billion at the time when this was figured out, 4 billion unique IP addresses sounded like a lot. There would never be that many devices. But as we know today, everyone has computers, everyone has phones. The number of devices that would use an IP address has far exceeded 4 billion at this point. So just from a networking point of view, it is not possible to give every device in the world a unique IP address. There just are not enough addresses available. In IPv6 is different, but for right now, let's just continue talking about IPv4 because that's predominantly still the standard protocol for the internet. So going back to our original example, you might have a phone, you may have a couple PCs at your home that are all connecting to a single router. We know now that it's not possible for the internet service provider, or whoever that may be, to give each of these devices their own IP address. There just aren't enough IP addresses that exist to be able to do that. But these still need to be able to connect to the internet somehow. And if you've seen in our previous videos, when you're doing routing, you can't have any IP addresses that are the same. They have to be unique IP addresses across the network. So that kind of seems like a sort of contradiction there. Like, how can you have all these unique devices with a smaller set of IP addresses available than what's required? And it seems like that just can't happen. Well, that's where network address translation comes into play. So in this case, instead of the internet service provider giving each of your devices a unique IP address, it's going to give your router one unique IP address. Now, that sounds a bit strange because one unique IP address does not help you route to these. How are you going to be able to share one IP address between all these machines, however many there may be, because we know that they have to have unique IP addresses? Well, the solution to that is we're going to take this part of the network, which is our LAN, and assign each of these machines what's called a private IP address. And there's several different private IP address spaces. Most predominantly, probably one that you most recognize is this one here. 192.168.something.something. Any address that begins with these numbers, 192.168, is considered to be a private IP address, which means that it is not able to be routed to the internet. So if you try to connect your computer to an IP address 192.168.something.something, it's not going to route it through the internet. It's only going to be contained within a LAN. What happens instead is your router is going to take information from this LAN and send it out through the single shared IP address. And the way it's able to do that is through a process called network address translation. So let's say this packet wants to talk to the internet, or this computer wants to talk to the internet. So it sends a packet out on its local address space. So let's say it's 192.168.0.5. That's the IP address for this computer, okay? It sends it up to the switch, which sends it up to the router. The routers, this particular interface on the router would have would be considered the gateway address for that network. And it would probably have an address like 192.168.0.1. So this has .5, this has .1. What your router is going to do then is it's going to take a note, basically, of what this computer is trying to do, what it's trying to access, and what kind of information it's probably going to expect in return. It's going to save that information, and it's going to take this IP address that it got from this computer, remove it, and replace it with the address given by the internet service provider. It then sends that out to the internet. So now that we have a computer that's requesting from some information, the router knows if the internet talks back, if it responds with information that is related to this request, it knows that this computer is the one that requested that information, and it's able to take that and send it back down to the PC here. The same is true for any of these PCs. Essentially, the router is keeping track of what packets are being sent by what machines down here, where they're trying to go, what kind of information they're trying to get back. And through this process, essentially, the router is able to take this whole address space, this whole private address space, and share it on a single IP address that's available on the internet. So from our network's point of view, our LAN's point of view, all these machines can be talking to the router, sending traffic back and forth between the internet. And from the internet's point of view, all of this data that's happening, or all this traffic that's originating down here, from the internet's point of view, is all coming from the same IP address. From what it sees, it's all seeing this traffic coming from the single shared IP address that was given to this router. So ultimately, the takeaway from this is, even though there is a limited number of IP addresses available on the internet, we're still able to make do basically with a workaround, which is network address translation, where we're able to conserve a lot of the IP address space and instead use the router, lean on the router some more to do more work, to keep track of the data going to and from machines, so that this router only needs to have a single outgoing IP address. It doesn't have to have one for each one of these machines. But one thing to keep in mind is that the router, in order for this to work at all, in order for it to be able to use all these machines and multiplex the data so that it's able to use it through a single IP address, the router has to know a lot about what the machines are trying to do, where they're trying to go, and what it's trying to receive. What that essentially means is that when a PC sends a request to the internet, it goes up to the router sees that this machine is trying to access this website on this specific port, and it keeps track of that. So when it sends it out to the internet, and the internet gives a response, wherever that response may come from, the router knows that this PC is the one that's looking for the traffic. So you can see from here, and in the previous example as well, the traffic is always originating from inside of the LAN. This would be the LAN here. So the traffic that's destined for the internet is always originated by these machines. And that's how the router is able to keep track of what's trying to go where and able to interpret the response from the internet. But what happens if the internet initiates the first contact? It's instead of the PCs trying to talk first, let's say the internet tries to talk first. Well, now you've got incoming traffic coming to a single IP address. Let's say it's just 10.0.0.10. That's not actually a valid internet IP address. That's actually classified as a private IP address space, but let's not get into that. Let's just say that everything on this network is trying to use this single IP address. So the router has to keep track of what machines are trying to talk to what and all that. So when it receives a response, it knows where to send the response in this local area network. But if a request comes in from the internet that was not originated by these machines, and it gets to the router, where's it going to go? As far as the router is concerned, none of these machines have initiated contact with that request. So the router receives this and sees all these machines down here that it could send it to, but it doesn't know which one to send it to. And instead of it sending it to every machine, what it does is instead just drops it. It just disappears. The router accepts it. It sees that none of these machines down here were asking for this, so it doesn't even send it. It just disappears. But let's say that there's a situation where you would want that traffic to go somewhere. Let's say you have a server on this network as well. And everything in this network still is on the same local area network. And let's say somewhere on the internet, wherever that may be, some person's trying to access this server. Let's say it's, a web server. So it'd be running on probably on port 80 or port 443. Doesn't matter. This person and this computer is connected to the internet somehow, usually through a setup like this. This person is sending a request up into the internet, which is directed at your router and your router's shared IP address. And this PC is making a request on port 80 for web traffic. Well, same as before, your router is going to receive this request, and it's not going to know where to send it because the server didn't initiate the contact. It was this person over here that initiated it. So there's no record in the router for anyone trying to access this server. So it receives this packet, doesn't know where to send it, and drops it. So that's where port forwarding comes into play. What port forwarding does is it tells the router, okay, any traffic comes in on a certain port, let's say port 80. So that's our web port. We're telling our router that if any traffic comes in that we didn't request from down here, if any traffic comes into the router with port 80 as the destination port, is to send whatever traffic that is down to a specific machine. In this case, it's our server. So any traffic, any web traffic, the router is to send it to this server, even if it has not initiated the contact. So what happens in this case is the same as before. Our person over here wants to try and access this server down here. And because this is behind a NAT, this is a non-routable private internet address space. So the server's IP address may be something like 192.168.0.10, something like that. Doesn't really matter. The point is, this address is not routable on the internet. You can't go to your PC, type in this IP address, and expect it to be able to go to the internet, to this router, and down to here. It's just not going to happen. What's going to happen is this PC is going to try and find it within its own local network, and when it can't, it's just going to disappear. Instead, what this person has to do, is it has to send a request to this router's shared IP address for this network, which may be like, just stick with the old example, even though it's not actually a real IP address, let's just pretend it is. So this person down here is actually going to type in this IP address, which is this port's IP address, into their web browser. Their PC is going to send a request up to the internet. Internet's going to send it to this router's port, the shared address port. Well, because he made this request on port 80 for web traffic, our router now knows, well, instead of getting rid of this data, what I'm going to do instead is, because this is not initiated from anywhere inside here, our default rule is to then send it to this machine here, to this server. So it would go from this PC to the internet to the router. The router would automatically send it to this server based on the incoming port. It would go down to the switch, to the server, and that's how this PC would make contact with this server. So if that seems complicated, don't feel bad, because it absolutely is. It is very complicated, and the exact nature behind how NAT works is very complicated in terms of how it's able to keep track of packets and sessions and all that kind of stuff. This is mainly just an overview to show you what port forwarding is actually doing, and to understand that you have to understand NAT at least a little bit. So hopefully you understand port forwarding is a option on the router for incoming requests. So if you get a request from the internet on a certain port, you can tell the router to send that request to a certain machine on that network.